Good morning, one and all. So, in the last class, we have started with the first type of digital modulation technique called as binary phase shift keying or BPSK. So, binary means we transmit only two symbols. So, obviously, they should be 1 and 0. So, for 1, we transmit S1 of t, that is nothing but root EB into phi 1 of t. For 0, we transmit S2 of t, that is minus of S1 of t, or that equal to minus root EB phi 1 of t. So, since these two are not independent, only one is independent, other one is dependent. So, we need only one basis function. Now, this is what the basis function is. So, here we multiply this basis function with root of 2 by TB. So, why? Because as I told you already in the last classes, every basis function should have a unit energy. So, you try to find out the energy of this basis function, you will get 1. Okay. So, here square root of 2 by TB should be there. Okay. So, this is what about the first basis function. Only one basis function we have, and these are the signal vectors, not vectors, points, because it is one dimensional, simply a straight line. So, this is the constellation diagram or signal space diagram, which includes the message points, and the distance between these two message points is 2 times of root EB, and the square of the distance is 4 EB. Now, so these are the two waveforms, S1 of t, S2 of t, and these are the BPSK waveforms. So, this is for taking cos, this is by taking sin theta, something like that. So, this is what we have. We have a phase shift of 180 degrees or pi radians whenever binary state changes. Otherwise, whenever 1 becomes 0 or 0 becomes 1, so there is a phase shift of 180 degrees or pi radians. Now, these are all the figures. So, you just go through them once. So, let us go to the one of the important aspects of any modulation, that is a generation or transmission of BPSK. Now, so first of all, we get a digital data, that is nothing but sequence of ones and zeros, 1 0 something like that. Now, it has to be encoded. Now, so if encoded, it becomes like this. Okay. So, here, so there are so many varieties of encoders. This is called NRZ encoder, NRZ transfer, non-return to 0. Here, so suppose 1 0, I can write like this also. This is 1, this is 0, this is 1, this is 0. I can write in this way also. This is 1, 1 for 1, 0 means 0. So, it is one way of writing the same data. Okay. Now, we can also write like this. 1 means 1, 0 means minus 1. It is one more way of writing the same data, or so one more way of representing the same digital data. It is called non-return to 0. So, in this type of representation, what we do is 1 means plus 1, 0 means minus 1 generally. So, this type of representation is called as non-return to 0 representation. Now, here, so I have represented in the form of NRZ. 1 means root EB, I am taking root EB. 0 means minus root EB. Okay. So, what is EB actually? It is a transmitted signal energy per bit. I told you already. Okay. Now, so this is simply the product modulator. So, this is the phi 1 of t. Now, suppose if 1 is transmitted, suppose you are transmitting symbol 1, means what is amplitude of 1? Root EB. Now, that is being multiplied with phi 1 of t. So, here what do you get? For symbol 1, you get root EB into phi 1 of t. Next, suppose you are transmitting symbol 0. For symbol 0, what is corresponding amplitude? Minus root EB. Minus root EB into phi 1 of t for symbol 0. So, just now I showed you. So, this is what is being, these two are generated. Okay. So, when you transmit symbol 1, you need to generate root EB into phi 1 of t. So, when you transmit symbol 0 or bit 0, you need to generate minus root EB phi 1 of t. So, same thing is being generated You just observe carefully. Here S of t can be root e b into 5 1 half t or minus root e b into 5 1 half t, depends upon which symbol is being transmitted. So this is simply the transmitter of BPSK or the generator of BPSK. So simply we have encoder followed by a product modulator or product multiplier. Okay, so it is something like carrier. Clear? So message signal is multiplied with the carrier, you are getting a modulated signal. Okay, now so let us move on to the another topic that is called correlator. Okay, so what is a correlator? So it is nothing but a product integrator, which means, so we take x of t, multiply with some basis function phi j of t, and we do integration. Okay, now what is xj? It is integration 0 to t of what? X of t into phi j of t. You just write down what is xj from this figure. That equal to integration 0 to capital T x of t into phi j of t dt. So this is a product as well as integration. So that's why it's called product integrator or simply called as correlator. Okay. So why it is so important? Now here, so let me go to the basic diagram of digital modulation. Here I told you. So this is what I told you just now. Encoder followed by modulator. So every source gives you some symbols. They need to be encoded and they need to be modulated. So they need to be transmitted over a channel, obviously. Now in the receiver part, you receive x of t. Now receiver has got two blocks, namely a detector and followed by a decoder. Okay. So now we have to discuss what is the detector and what is the decoder. We have done with modulator. As for BPSK at least we have done for modulator, isn't it? Just now explained. Now we have to see how to design the receiver of BPSK. Okay. Now it has got two important blocks, that is detector and decoder. So this finally this estimation. Okay. Suppose you have transmitted MI, M cap is the estimation. So if M cap is equal to MI, there won't be any error. Otherwise there will be an error. Anyway, now so here to this correlator, what is the input? Input is x of t, that is the received signal. Okay. So now what is x of t? Obviously that is SI of t, that is transmitted signal, plus W of t is a noise. What kind of noise is that? AWGN noise, means additive wide Gaussian noise with a zero mean and power spectral density N0 by 2 or eta by 2. So as I told you already, so when we are dealing with the analog modulation schemes, we have taken PSD of noise as eta by 2. Here we take N0 by 2. Okay, so these are two different representation of the PSDs of the noise. Either you can use eta by 2 or N0 by 2. Both are alright. So in case of analog techniques, I have used eta by 2. Now in the digital, I will write N0 by 2. Okay. So with the PSD N0 by 2 with a mean 0, W of t is a AWGN noise. Now what is x of t? It is a transmitted signal or a modulated signal plus noise. Obviously, noise will be added in the channel. Okay. Now, so this is the detector. This is what the detector. Okay. Now here, so just now I told you this is the correlator. Now here we have n such correlators. How many? Capital N number of correlators. So that is called a bank of n correlators. We have a bank of n correlators. So it is nothing but a detector or simply a demodulator. This is the simply demodulator of BPSK, not BPSK in general. Okay. So this is the in general demodulator of any digital modulation techniques. What happens here is, so x of t is input to this block of n correlators. Now first of all we are multiplying with phi 1 of t and we are doing integration. You get x1. Next, this for x2. It is for so on xn. Okay. So this x1 is the output of first correlator x2 is output of second correlator, so on, so on. xn is output of the nth correlator. So we have a bank of n such correlators. Okay. So why n? N is the number of basis functions. Here I am not talking about BPSK, I am talking about in general digital modulation technique. So if there are n number of basis functions, we should take n correlators. So x of t is a common input to the bank of n correlators, and each and every correlator will give you some output. Now, so all these are simply called as capital X. What capital X contains? It contains x1, x2, so on, so on, xn is a vector. Now input is a time domain signal x of t, output is a vector, column vector capital X. So this is what the detector will do. I told you already. It is nothing but vectorization will happen. Input to the detector is x of t, output is capital X is a vector. So x of t is a time domain signal. So whereas capital X is a vector, it contains something like this matrix, a column matrix. Here what x contains? x1, x2, so on, so on, xn. Outputs of each and every correlator, n such correlators. So this is a detector also called as demodulator. Okay. Now, so I am discussing in general demodulator, not about BPSK. We'll come to BPSK later. So, but let me simply discuss the generalization of detector or demodulator. Okay. Now, so what is xj? Output of jth correlator is simply just now I told you here. What is xj will be now? So integration 0 to t x of t phi j of t dt. But what is x of t? Si of t plus w of t. What is w of t? Is a noise process. Si of t plus w of t phi j of t dt. You just simplify this. So what do you get? Integration 0 to t Si of t phi j of t dt plus integration 0 to t w of t phi j of t dt. So you know already what this means. What is it? Sij. They are coefficients of expansion. Now what is this? We are simply calling it as a Wj. Okay, where j varies from 1 to n. What is capital N? The number of basis function. Here please remember, I am repeating, the capital M is the number of transmitted signals. S1, S2, so on, so on, Sn. What is capital N? The number of basis functions. Phi 1 of t, phi 2 of t, so on, so on, phi n of t. So phi j of t is a noise sample. So what is W of t? Is the zero mean and the variance sigma square. So with a just now I told you with the PSD n naught by 2. So we know already the power spectral density and the autocorrelation function are Fourier transform pairs. Now this is the autocorrelation of the noise. Expectation of W of t, W of u, that equal to RW of t minus u. This is a time shift. So this is the autocorrelation of the W of t. This is a time shift. Otherwise we can write RW of tau equal to n naught by 2 delta of tau. Tau is a time shift. So it is because of wide sense stationary noise process. So what is mean by wide sense stationary? So I have explained in detail while discussing PTSP. So please go through it once. Here, so the power spectral density of noise is n naught by 2 and the autocorrelation function of the noise is n naught by 2 delta of tau, or so n naught by 2 delta of t minus u. What is t minus u? Is a different time instances. T is one time, u is another time. So these two are Fourier transform pairs. So if you take the Fourier transform of this autocorrelation, you get the power spectral density and vice versa. Okay. So I hope these things are very clear to you. But remember, what is xj equal to now? The output of jth correlator is Sij plus Wj. So please remember this. The output of, what is the output of first correlator x1? What is x1 equal to? How do you write x1 equal to? What is x1 equal to? Si1 plus w1 because j equal to 1. Si1 plus w1. What is x2? Si2 plus w2. So on, so on. Okay. But you just remember what is Sij. This is the coefficient of expansion. What is the formula of Sij? This is the formula of Sij. Sorry. This is the formula of Sij. So because I told you this formula while discussing the Gram-Smith orthogonalization procedure. Okay. So just now I am telling you one more time. Without knowing the signal space analysis, you cannot do anything in the digital modulation techniques. So at least now you just go through those third chapter signal space analysis. Okay. Now here we have to find out the mean and variances of output of the correlator. Here, so these are very, very important. So this is the first part of the receiver. I told you the first part of the receiver is the detector. Okay. So what detector will do? It converts x of t equal to x of t to capital X, a vector. So the vectorization will happen here. Here, so these are outputs we have. We have to find out what is these are also random variables. Okay, Gaussian random variables. Because x of t is a Gaussian now. I mean x of t is Si of t plus W of t. W of t is a random process, Gaussian random process. Obviously x of t has also random process, Gaussian random process. Now here, so we have to find out what is the mean and variance of each and every output of the n correlators. Okay. So we have to find out what is the mean of x1, mean of x2, so on, mean of xn, and what is the variance of all these outputs. Okay. But we know that what is xj, that is Sij plus Wj. Here Sij is simply a constant. Okay. So these are the coefficients expansions. So coefficients of expansion. Okay. Here Wj is a random in nature, but Sij is simply a constant. Okay. Now, so mu of xj, what is the mean of xj? That is expectation of xj. But what is xj? Sij plus Wj. So Sij is simply a constant. Okay, this is something like a into x1. No, we say x1, a is a constant, something like that. Okay, they are coefficients, simply the coefficients. They are not random variables or random process. Whereas this Wj is a random sample of random process. Now, so we know already expectation of some constant plus x, that is nothing but a plus expectation of x. So these are all properties of expectation. So I hope you are okay with all those properties of expectation. Now it is Sij plus expectation of Wj. What is expectation of Wj? It is 0. Why? Because just now I mentioned, what is that? W of t has a 0 mean and the variance sigma square. So that's why the mean of Wj is 0. Simply the mean of xj equal to Sij. Okay. Now remember, it is a conditional mean. Why? Because so Sij depends upon both I value as well as j value. It depends upon both. So here we should know the value of I and the value of j. So which means we should know what symbol is transmitted and what vector is received. It is something like conditional. So we should know xj what is received given that what is transmitted. So both should be known to us, something like conditional. Okay. Now this is a mean. Mean is a constant. What is the variance? So we know variance formula. Expectation of xj minus its mean whole square. What is the mean of xj? Sij. But what is xj minus Sij? Xj minus Sij. What is that? Wj. Correct? So expectation of Wj square. So here this is what expectation of Wj square. The simple calculations, finally it becomes n naught by 2 delta of t minus u. Okay. Here what I have done is, so expectation of Wj square, no? So Wj I am writing, what is Wj? W of t, phi j of t dt. This is one thing. Next I have changed the variable. I am writing u variable. Here the variable is t, here the variable is u. This is one Wj, it is also another Wj. I have taken different variables. Here the variable is t, here the variable is u. That's it. Now I have written like this: integration 0 to t, integration 0 to t, phi j of t, phi j of u, w of t, w of u, dt du. So interchanging the order of integration and expectation, because phi j of t, phi j of u they are deterministic signals. They are not random signals. Why? Because these are basis functions which you have found out. They are not random, because we know what is the shape of the basis functions. What is random? This is random. So we keep them outside the expectation because they are known signals to us. So we are applying expectation to only W of t, W of t. What is this? This is nothing but autocorrelation. Just now I told you. Okay. Now, so this is Rw of t comma u, or Rw of t minus u, that is n naught by 2 delta of t minus u. So one more thing. So we can also write Rw of t comma u. This is also one more way of representing the autocorrelation function. Rw of t minus u or Rw of t comma u. Anything is alright. But what is that? N naught by 2 delta of t minus u. I am substituting here. So n naught by 2 delta of t minus u. N naught by 2 outside integration. This is what we have. Okay. So this is what we have. Finally, so this is from the properties of delta function. So it is defined when it is defined if and only if t equal to u. Okay. When t equal to u, it is non-zero. Otherwise it is 0. When t is not equal to u, it is 0. I hope you are okay with this simple explanation of delta function. When t equal to u, this will be 1. So when t equal to u, phi j of t again. So integration 0 to t, phi j of t whole square dt. What is this? That is energy of basis function, that equal to 1. So you are left with n naught by 2. So sigma phi j square equal to n naught by 2 for all j. So otherwise we don't need to do all this calculation. Simply here what you got? This is what the expectation of Wj square is, nothing but variance of Wj or variance of W of t. What is the variance of W of t? You just find out the variance of W of t, that is sigma square. Okay. Now, so simply, so this is very, very important. So all the correlators outputs have a variance equal to power spectral density of the noise process W of t. Okay. So the variance of the output of the correlators is equal to power spectral density of the noise W of t. And furthermore, each and every output is having same variance. Okay. So let me summarize this like this. So here we have a bank of, here I have a bank of n such correlators. So the mean of each and every correlator output is different. What is the mean of x1? What is the mean of x1? Si1. Mean of x2? Si2. Sin. So each and every output is having different means, but all outputs are having same variance. How much is that? N naught by 2. That is also equal to power spectral density. Okay. So the n outputs of the bank of n correlators having different means, but they are having same variance, that equal to n naught by 2, we know that that is also equal to power spectral density of the noise. So the variance derivation is very, very simple. So this is a simple derivation. You just go through it. This is simple mathematical calculations. So this is not at all difficult. Okay. Now, so we are done with the mean and variance of the output of each and every correlator and such correlators. Now let us find out the covariance of outputs of the correlators. Covariance formula we know already. So this is what you get. So the what a covariance formula? Xj minus mean, its mean. Xk minus its mean. So what is the mean of Xj? Sij. Mean of Xk? Skj. But what is Xj minus Sij? Wj. What is Xk minus Skj? Wk. But what is Wj? This is what we Wj. What is Wk? This is Wk. Again same. Just write down separately. Apply the expectation to the terms which are relevant. Here phi j of t, phi k of u are known signals. They are not random signals. So that's why keep them aside. Apply the expectation to the signals which are random in nature. What are random in nature? W of t, W of u, because they are noise processes. So again, this is nothing but the autocorrelation function. This is the autocorrelation of the noise process. So this is what you get finally. Here, so obviously, so what do you get? So you take one integration. So this is non-zero when and only t equal to u. If and only if t equal to u, this is non-zero. Okay. If t is not equal to u, this delta function will be 0. Everything will be 0. Why? Because so you know already delta of t is defined only when t equal to 0. When only t equal to 0. These are the properties of delta function, Dirac delta function. So when t is not equal to 0, this will be 0, which means, so in place of t, generally I have t minus u. So whenever t minus u equal to 0, this is defined. So when t is not equal to u, this delta function will be 0, entire function will be 0. So when t equal to u, so this is what you get. Okay. What is happening here? So this is when t equal to u, what is happening? So this will be 1. So phi j of t, phi k of t. Please make a note of this. I am not changing j, k. I am changing t and u. T becomes u. T equal to u. Not j is not equal to k here. So they are subscripts. So phi j of t, phi k of u. T and u are time instances. So this is defined. This will be non-zero if and only if t equal to u. This is a property of delta function. When t equal to u, what do you get? Phi j of t, phi k of t. So this becomes 1. We are left with only one integration. This is what you get. N naught by 2 integration 0 to t, phi j of t, phi k of t dt. So now, when j is not equal to k, this is also 0. Why? When phi j means jth basis function. Phi j of t means jth basis function. Phi k of t means kth basis function. These are two different basis functions. So what is the integration of two different basis function? It is 0. Why? Which property? Orthogonality property. All the basis functions are orthogonal to each other. Whenever j is not equal to k, it is also 0. When j equal to k means same basis functions. When j equal to k, so what is this becomes? Integration 0 to t phi j of t whole square, that equal to 1. This is n naught by 2. But so when j is not equal to k, so these are two different basis function. So their inner product will be 0 because they are orthogonal. Okay. So when j is not equal to k, so this is 0. What is 0 finally? Covariance is 0. Please remember, I have started with covariance of xj, xk. When j is not equal to k, obviously it has to be true. When j equal to k, this is not a covariance, no? When j equal to k, what happens? This is simply variance. When j is not equal to k, we are finding the covariance of xj, xk. What do you got? Finally, 0. Okay. So it is obvious j should not be equal to k, because we are finding the covariance of two different symbols, isn't it? If j equal to k, what happens? It becomes variance. Why? Because xj, this becomes whole square. So it is variance. Okay. That becomes n naught by 2. Just now I found out. Here also, if j equal to k is this quantity is 1, it is n naught by 2. Now here the covariance of the outputs of the bank of n correlators is 0. If the covariance is 0, they are independent. But the converse will not be true. I told you already. So if the covariance is 0, they are obviously independent of each other. What are independent? Statistical independent. Here, see, we are dealing with these outputs of the correlators x1, x2, xn. They are having different mean values. They are having same variance n naught by 2. That is also equal to power spectral density. But finally, the covariance of all these elements is 0, which means all these elements are independent of each other. x1 is independent of remaining elements, x2 is independent of remaining elements, so on so on, xn also independent of remaining elements. All the outputs of these n correlators are independent of each other. Why they are independent? Because the covariances are 0. Okay, so that is the conclusion. Now, so here I am writing, since xj's are Gaussian random variables, they are Gaussian random variables, so defined in the vector form. So this is what the vector capital X. It contains n elements, namely x1, x2, so on, xn, with order n cross 1. Now, what is x is called? It is called a observation vector or received vector. Now, what is the properties of this vector? It is a column matrix with elements x1, x2, xn. What are these elements? Outputs of the correlators. Now, how are they? They are Gaussian random variables. They are having a mean of Sij, variance of n naught by 2, that is same for all, and furthermore they are independent of each other. Now, here, so we have to write the conditional PDF of the vector x. Okay, so what we have to write? We have to write the conditional PDF of this vector x. But how to write this conditional PDF of this vector? But this vector contains n elements. Okay, we know the properties of these elements. We know the statistical properties of these elements. What do we know about these elements? We know the mean of these elements and the variance of these elements, and furthermore we also know that they are independent of each other, and we know that they are Gaussian random variables. Okay. Now, so I want to know what is the conditional PDF of this vector. See, conditional means vector x is received given that some symbol mi is transmitted. Always everything is conditional here. Why? Because we don't know what symbol is transmitted. We have m such symbols. We have capital M number of symbols. We don't know what is transmitted generally. Okay. Now, so here I am making this statement. Please pay your attention. This is very, very, very important statement. So to find out the conditional PDF of the vector x given mi is transmitted, I want to write the conditional PDF of vector capital X as a product of conditional PDF of the element xj, which means in simple words, so the conditional PDF of this vector x is equal to conditional PDF of vector x element x1 into the conditional PDF of element x2 into so on the conditional PDF of element xn. How can I do so? I can do so because they are independent of each other. So vector x contains n elements, but those n elements are independent of each other. That's why, so the conditional PDF of this vector equal to the product of individual PDFs. Okay, so this is what the statement says. So the conditional PDF of this vector capital X equal to the product of the conditional PDF of individual elements xj. Okay, you expand this, what do you get? Fx of x given mi equal to fx1 of x1 given mi into j equal to 1 to n into x2 given mi, x3 given mi, so on xn given mi. Here I is fixed actually. I varies from 1 to m. Please pay your attention here. Okay, it is a conditional. What condition? Mi means ith symbol is transmitted. What is about condition? Condition about capital X. Okay. So this is about the conditional PDF of the observation vector capital X or received signal vector capital X as a product of individual conditional PDFs. We can write so because all these are independent elements. Okay, so you try to understand this by reading the basics of probability. Okay, so we stop here. So thank you.